Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked about our cosmic neighborhood. Why do all the planets in our solar system orbit the sun on the same flat plane and in the same direction? Is this a massive coincidence, or did something profound happen to make it this way? And if there was a process, do we have evidence of it elsewhere in the vast tapestry of the cosmos? But don't worry, we'll take it slow. This isn't a race through equations or rigid scientific lectures. It's more like floating through a galaxy of ideas with a cup of chamomile tea, allowing your mind to gently embrace the wonders of the universe. We'll let these grand questions gently guide us like a calm river leading us through breathtaking landscapes. Let us drift slowly into this idea like a small boat upon a still lake. When we imagine our solar system, a picture often blossoms in our minds: a flat disk adorned with countless rings, each one a silent pathway for a planet. This is an image we've learned since childhood, a concept so deeply woven into our understanding that we simply take for granted the notion that all planets lie on the same orbital plane. It's as if a grand cosmic artisan carefully laid out a collection of glass marbles upon an immense smooth table, each one destined to roll along its designated path with serene precision. This elegant arrangement, where every celestial body seems to follow a harmonious, unspoken agreement, is often overlooked in its profound simplicity. Yet the quiet wonder deepens further. Not only do they share this communal table, but every single planet, from the fiery embrace of Mercury to the distant icy whispers of Neptune, also orbits our sun in the very same direction. Imagine this not as a mere collection of marbles, but as an enormous silent cosmic clockwork where every gear, every delicate mechanism turns in unison, a breathtaking ballet performed without a single misstep or discordant movement. Have you ever truly pondered why this might be so? Is it an extraordinary, almost impossible stroke of cosmic luck, a grand lottery win in the vastness of chance? Or is there a deeper narrative, a primordial event, a fundamental process that sculpted our universe into this remarkably orderly fashion? And if such a formative process truly exists, might we find its subtle, echoing fingerprints elsewhere, shimmering in the light of distant stars or hidden within the swirling nebulae of other galactic realms? These questions, though seemingly simple, are like gentle tugs on the very fabric of our understanding, inviting us to look beyond the obvious and seek the hidden truths. As you might already intuit, this elegant uniformity is not, in fact, a colossal cosmic coincidence. The universe, in its most profound moments of creation, rarely indulges in such random extravagance. Instead, it tends to unveil astonishing patterns and underlying principles, subtle yet powerful signatures of the events that have shaped its boundless expanse. This inherent tendency towards order, this silent rhythm, is not unique to our solar system. Consider, if you will, the regular moons that gracefully attend the gas giants within our very own cosmic neighborhood. These smaller celestial companions, seemingly miniature versions of our planetary family, also faithfully orbit their massive hosts on the same flat plane and with astonishing consistency in the same precise direction. It's as if a symphony of cosmic creation plays out across different scales, a repeating motif of harmony and design. Take for a moment the breathtaking sight of Saturn's magnificent rings. These dazzling celestial halos, composed of countless icy particles and rocky fragments, are not merely scattered haphazardly about the planet. Oh no, they too, with an exquisite, almost mesmerizing precision, orbit Saturn along the very same plane as its regular moons. Their movements are a testament to beautiful clockwork precision, each particle, each moonlet, dancing in perfect, predictable harmony. So you see, the evidence abounds. There are countless examples of this remarkable ordered arrangement, but the deeper questions linger echoing softly in the quiet spaces of our minds. How and why did all of this come to pass? To truly begin to unravel this grand tapestry of cosmic order, we must gently turn back the hands of time, billions of years ago, to a period long before the comforting warmth of our sun first graced the cosmos, to the very moment of our solar system's nascent stirrings. Let your mind gently drift back to that distant past, a time when space-time was still a vast, unblemished canvas, patiently awaiting the first delicate brushstrokes of life and structure. We shall journey to explore the profound mysteries of beginnings, the humble, unassuming gas and dust particles that eventually coalesced and intertwined to forge the vibrant, complex worlds we recognize today. This is not merely a scientific exploration, but a poetic narrative of transformation, a grand tale of emergence from chaos to order, from the lonely scattered specks of matter to the resplendent planets and majestic stellar systems that populate our universe. In this serene voyage, we will not chase definitive answers, for the cosmos delights in its lingering enigmas. Instead, we shall celebrate the inherent beauty within the very act of questioning. We will allow our curiosity to take wing and soar, freely embracing the humbling truth that there are boundless aspects of the universe that remain beyond our current grasp. And it is precisely within these vast, shimmering realms of mystery that we uncover the most profound sense of awe. Let these contemplations gently guide you towards slumber imbued with a tranquil sense of peace and a deep intrinsic connection to the immense, wondrous cosmos of which we are by a miracle of happenstance an intimate and integral part. Consider the countless stars that dot the velvet expanse of the night sky, each a distant, shimmering beacon. It is a wondrous thought that each of these stellar embers could very well be the luminous heart of another solar system, complete with its own retinue of planets and moons, all performing a similar cosmic waltz, obeying the very same fundamental laws, echoing the harmonious ballet we observe in our own celestial home. Perhaps what we witness here, in the comforting familiarity of our cosmic backyard, is but a miniature echo, a tender replication of a grander, more universal pattern, a magnificent, intricate cosmic dance unfolding ceaselessly across the entire boundless cosmos. The sheer scale of this recurring pattern, this consistent rhythm of creation, invites a profound sense of wonder, a quiet realization of the universe's elegant underlying order. This astonishing arrangement, the flat disk of orbits, the synchronized movement in a single direction, is far more than a mere peculiarity of our own solar system. It is a pervasive signature, an indelible cosmic fingerprint, subtly yet powerfully imprinted across the vastness of creation. It speaks volumes of fundamental principles, perpetually at work, diligently shaping everything, from the most minuscule, unassuming particles of dust to the most colossal, breathtaking galaxies. And it is precisely in the gentle act of discerning and acknowledging these grand overarching patterns that we begin to truly comprehend the profound complexity and unparalleled beauty that define the universe. It is a quiet symphony of physics played out on an unimaginable scale, revealing a hidden artistry in the dance of matter and energy. So as you settle in, gently close your eyes, take a deep, calming breath, and allow this story to softly transport you on a journey through the boundless reaches of space and the infinite currents of time. This is not a journey with a fixed destination, but rather an ongoing exploration, an unending wellspring of wonder, and a profound sense of tranquility that washes over us as we acknowledge our humble yet integral place within this immense, extraordinarily beautiful cosmic tapestry. We shall commence our story from a place of profound stillness, a distant realm where matter itself had yet to assume its intricate forms, where countless particles of gas and ephemeral dust patiently awaited a signal, a subtle shift, to embark upon an irreversible chain of reactions. It is a captivating tale of cosmic inception, of the tiny potent seeds of life, an intricate structure being gently sown into the tender nascent fabric of a young universe. This nascent universe, a vast swirling canvas of potential, was poised on the brink of an extraordinary transformation, ready to bloom into the rich complexity we observe today. Imagine, if you will, a cosmic nursery, a celestial garden where new stars are meticulously cultivated and brought into being. Within these ethereal glowing havens, matter is in a constant, graceful state of flux, ceaselessly moving softly, colliding, and patiently combining. And it is precisely from this initial seemingly chaotic dance of creation that a new order slowly, meticulously begins to emerge, an order that we can now observe with such startling clarity and profound appreciation within the exquisite confines of our own solar system. This emergence is not abrupt, but a gentle unfolding, like the slow blooming of a cosmic flower. The serene flatness of the orbital disk, the harmonious synchronization of all movements, these are not accidental features. They are, in essence, the inevitable culmination of a profound process of self-organization, a magnificent cosmic ballet orchestrated by the universe itself, without the need for any external guiding hand. It stands as a powerful testament to the inherent, almost intelligent capacity of matter to fashion intricate and resplendent structures from the most fundamental and unassuming of beginnings. It is a quiet, elegant affirmation of the universe's innate drive towards complexity and beauty, a testament to the fact that even in the vast emptiness, profound order can arise. And as we embark on this contemplative exploration of our cosmic narrative, let us softly remember that we are not merely delving into the realms of physics or astronomy. We are, in a far more profound sense, learning about ourselves, about our delicate and miraculous place within the grand scheme of the cosmos, and about the fundamental laws that have so meticulously shaped our very existence. Every solitary particle of dust, every majestic planet, every shimmering star, each is an intrinsic thread within a much grander interwoven story, a story that we are now gently, page by page, beginning to uncover and comprehend. Allow these thoughts to drift lightly through your mind, like wisps of clouds gracefully traversing the expanse of the night sky. There is no need to grasp or analyze them with forceful intent. Simply absorb their vastness and revel in their inherent beauty. And as you surrender to the embrace of slumber, carry with you this profound sense of wonder, this comforting realization that we inhabit a universe that is endlessly mysterious and breathtakingly miraculous. A place where even the most ordinary observations unveil stories of extraordinary cosmic creation. The formation of our solar system was not a sudden explosive event, but rather a slow, patient process stretching over millions upon millions of years. It was a gradual unfolding where each deliberate step was meticulously shaped by the foundational laws of physics. And it is within the deep, quiet patience of this colossal cosmic evolution that we discover a unique and profound beauty. The beauty of persistent change, of exquisite adaptation, and of the tireless dance between chaos and emergent harmony. This process, a slow unfolding of potential, speaks to a fundamental patience inherent in the universe itself. Imagine for a fleeting moment those tiny, unassuming particles of dust, those solitary gas molecules all drifting aimlessly within the boundless expanse of space, seemingly devoid of any inherent purpose or direction. But then, something subtle yet monumental occurred. A singular event, a gentle cosmic whisper, shifted the delicate balance, altering the course of everything and quietly sowing the seeds for the eventual formation of stars and planets. And it was precisely from that initial seemingly scattered disarray that a new profound order was born, an order that we continue to explore, marvel at, and draw endless inspiration from, even to this very day. This journey from the formless to the formed, from the scattered to the cohesive, is a testament to the universe's deep, almost intentional artistry. Let us now begin our gentle journey back in time, not with a sudden lurch, but with a slow, deliberate drift, billions of years into the cosmic past. We arrive at a moment long before the first whisper of our sun's warmth, a time when our solar system was nothing more than a potential, a mere thought, in the vastness of the universe's unfolding story. Deep within the heart of what astronomers fondly call an H2 nebula, or more poetically, a stellar nursery, lay an immense, sprawling cloud of gas and dust. This was a place of profound stillness, a silent, swirling ocean of primordial matter suspended in the cosmic void. Each tiny particle, a speck of dust, or a wisp of gas possessed an inherent resistance, an internal repelling pressure that subtly pushed back against the gentle persuasive pull of its neighbor's gravity. For eons, perhaps, this delicate balance held a quiet, almost imperceptible tension between attraction and repulsion, a moment of poised equilibrium in the cosmic dance. Then one day, a subtle, yet monumental event occurred. It wasn't a thunderous roar, but perhaps a distant, almost imperceptible ripple, an outside push of energy. Imagine the faint, ghost-like breath of a supernova, a dying star's final spectacular gasp, sending a shockwave silently rippling through the cosmic tapestry. This wave, a gentle but firm hand, jolted the tranquil gas and dust within our nascent nebula. It wasn't violent, not like an explosion in the traditional sense, but more akin to a gentle stirring of a sleeping giant. This subtle disturbance, this almost ethereal nudge, was enough to disrupt the delicate inward pressure that had held the particles apart. With that internal resistance momentarily weakened, the particles no longer held at bay found themselves drawn to one another. Like tiny curious children reaching out in the dark, they began to softly collide, to gently brush against each other, and in a profound act of cosmic intimacy to clump together. These were the very first whispers of creation, the tentative foundational building blocks beginning their long, intricate journey towards complexity. Soon these initial fragile clumps, formed by the barest touch of gravity, began to grow. Like tiny hungry seeds in fertile cosmic soil, they gently but inexorably attached to other clumps, gathering more and more of the ethereal gas and dust that drifted by. With each new particle that adhered, their mass slowly but surely increased. And with that increase in mass came a corresponding strengthening of their gravitational pull. It was a silent, self-reinforcing embrace. The more they gathered, the more powerfully they could draw in even more material. This process, slow and patient, unfolded over the quiet stretches of cosmic time. Within just a few thousand years, a mere blink in the grand eye of the universe, the gentle impacts from the ever-infalling material attracted by the growing central mass began to become more energetic. This increased friction, this constant gentle jostling, caused the burgeoning object at the very center of this gathering cloud to begin to heat up. It wasn't a sudden burst of warmth, but a gradual internal glow, like a quiet fire slowly kindling in the cosmic chill. More and more material from the surrounding nebula cloud, drawn by the intensifying gravitational embrace, was gently sucked inward, feeding this burgeoning core. This growing warming heart, this nascent stellar embryo, was what we now affectionately know as a protostar, a very young star still in its infancy, patiently gathering strength, its core not yet ignited with the roaring furnace of nuclear fusion. It was a promise of light, a star waiting to be born. In those earliest formative moments, the infalling material swirling around this burgeoning protostar would have been drawn in from every conceivable direction. Imagine a vast, chaotic swarm of cosmic bees, each flying along its own unique individual path, all converging upon a single irresistible point in the center. This created an incredibly chaotic environment, a swirling vortex of disorganized motion around the young protostar. Collisions between these countless particles would have occurred on a truly regular basis, a constant, gentle bumping and grinding in the cosmic dance. And through this incessant, almost methodical process of collision, a peculiar and profoundly important phenomenon began to unfold. The angular momentum of these wildly varied particles would have been canceled out. Think of it like dancers on a crowded floor, each spinning in their own direction. If two dancers collide, one spinning clockwise and the other counterclockwise, their individual spins might cancel each other out, leaving them momentarily still, or perhaps causing them both to drift in a new shared direction. In the cosmic ballet, this cancellation was key. However, these infalling particles, though seemingly arriving from all directions, did not approach with perfect uniform randomness. The collapsing nebula cloud as a whole, this grand cosmic swirl, possessed a total angular momentum, a pre-existing subtle spin that guided its overall collapse. So what gently, yet inevitably began to happen was this: while particles indeed approached from every conceivable angle, and many of their individual erratic momenta were cancelled out by particles moving in precisely the opposite directions, there remained a subtle underlying bias. Imagine a vast crowd of people all trying to move towards a central point, but with a slight, almost imperceptible leaning of the entire crowd towards one particular direction. After all the jostling, bumping, and canceling out of opposing movements, what you are softly left with is the predominant direction that most of the particles or people were collectively tending towards. It was like sifting through a wild storm of leaves and noticing that despite the individual twists and turns, the bulk of them are carried in a single overarching current. To help your mind gently wrap itself around this intricate concept, let me offer you a simple, yet profoundly insightful visualization. Imagine a sheet of lycra, stretched taut and smooth, representing the pliable fabric of space-time. Now, place a heavy ball or protostar in the very center of this sheet. Its substantial mass causes the lycra to sag, creating a gentle, inviting depression. This sag, this curving of the fabric, is our tangible representation of gravity, a force that in the vastness of our three-dimensional universe acts in much the same way, subtly bending and warping the invisible tapestry of space and time. Now picture tiny light balls being gently rolled across the lycra sheet. Some are rolled in one direction, some in another, some directly towards the central object. Dan Burns, a brilliant guide in these cosmic visualizations, demonstrates this beautifully. He gently throws small balls in various directions around the central heavy object. These balls, representing our infalling particles, begin to orbit within the gravitational well created by the heavy ball. Their paths are initially varied, some spiraling clockwise, others counterclockwise, some almost straight. But inevitably, as more and more balls are introduced, they begin to collide with one another. When a ball going in one direction meets a ball going in the opposite direction, their momentum, like two opposing forces, is canceled out. They might come to a stop, or they might bounce off in a new, often less energetic direction. What you are eventually left with, after countless such gentle collisions, are primarily the balls that didn't have a direct head-on collision to cancel their momentum, or those that were already aligned with the overall subtle spin of the sheet. Critically, these remaining balls are almost all going in the same direction, having shed the chaotic energy of their opposing counterparts. They now move in a harmonious, synchronized flow. Now it is important to softly note a subtle difference between our lycra model and the true cosmic reality. On the lycra sheet, friction would eventually cause the small balls to slow down and come to a halt. However, in the boundless, frictionless expanse of space, particles, once set in motion, tend to continue orbiting indefinitely unhindered by such terrestrial restraints. So imagine our cosmic particles continuing their eternal dance, unlike the lycra balls that eventually lose their energy. Furthermore, our lycra sheet is a kind of two-dimensional representation of what is actually happening in a three-dimensional plane within a vast four-dimensional universe. So, as you contemplate this, you'll need to gently stretch your imagination, envisioning these particles not just moving across a flat surface, but also along another axis, perhaps, swirling up and down as well. Instead of merely the two primary directions of approach visualized on the lycra sheet, imagine these cosmic particles approaching the burgeoning protostar from truly all directions within the three-dimensional space. They would gently, yet persistently, collide with one another, and through this constant, intricate cosmic dance of impact and rebound, their opposing momenta would continue to cancel each other out. It's a grand self-sifting process, a cosmic winnowing, where the chaotic, discordant movements are gradually subdued and eliminated. What ultimately remains, like the calm after a storm, is only the predominant direction of motion the collective spin that was inherent in the initial collapsing nebula. This gentle yet powerful process is the cosmic sculptor that gives rise to what is known as a protoplanetary disk. This disk, thin and pancake-like, is the birthplace of planets, a flattened swirl of remaining gas and dust, all gracefully orbiting the central protostar in a single harmonious direction. As more and more material continues to gently fall into the burgeoning protostar from this rotating disk, the subtle angle of these incoming impacts begins to impart a gentle spin to the protostar itself. In a remarkable act of cosmic synchronization, the protostar begins to rotate in the same direction that the disk is spinning. It's a beautiful testament to the interconnectedness of cosmic forces, where the disk influences the spin of its parent, the star, in a continuous, elegant feedback loop. This nascent solar system, now a swirling, flattened disk, is slowly settling into the ordered arrangement. We see today a peaceful outcome from a chaotic beginning. This gentle shaping, this subtle cancellation of competing motions, is a fundamental ballet of physics. It's like a colossal, invisible hand carefully spinning a giant potter's wheel. The clay, initially amorphous and scattered, gradually yields to the centrifugal forces and the steady, unwavering pull of gravity. As the wheel spins faster, the clay flattens and spreads outwards, forming a perfect symmetrical disk. In our cosmic analogy, the collapsing nebula is the formless clay, and the combined forces of gravity and angular momentum are the potter's hands shaping it into the delicate, swirling form of the protoplanetary disk. The reason for this flattening is simple yet profound. Any motion that is perpendicular to the overall direction of the disk's spin will eventually be canceled out. Think of it like a group of people dancing wildly. But if they are all trying to move towards the center of a spinning stage, any movement that takes them up or down from the stage surface will be met by opposing forces, eventually pushing them back onto the same flat plane of motion. This relentless process ensures that the vast majority of the remaining material coalesces into a thin, luminous disk, a cosmic dinner plate upon which the planets will soon dine. The energy lost during these collisions is not simply vanished. It is subtly transformed, often radiating away as heat, contributing to the warming of the nascent protostar and its surrounding disk. This constant dissipation of energy is crucial, allowing the system to shed its initial chaotic exuberance and settle into a more stable, ordered configuration. Without this mechanism for energy loss, the particles might simply rebound indefinitely, preventing the cohesive clumping and flattening that is so vital for planet formation. It's a gentle release, a cosmic exhalation, allowing the system to find its equilibrium. The protostar itself at this stage is still far from being a true star. Its core is not yet hot enough for the incredible pressures and temperatures required to initiate nuclear fusion, the process that powers our sun and all other shining stars. It is merely a very large, very warm ball of gas and dust, patiently accumulating mass and slowly collapsing under its own immense gravity. The protoplanetary disk around it, however, is a hive of quiet activity. Within its swirling expanse, gravitational instabilities begin to ripple, creating subtle pockets where the density of gas and dust is slightly higher. These denser regions act as tiny gravitational anchors, slowly, almost imperceptibly, drawing in more and more material from their immediate surroundings. It's like small eddies forming in a gently flowing stream, gradually accumulating twigs and leaves. This is the cosmic crucible, the gentle laboratory where the building blocks of planets, the planetesimals, begin to emerge. These planetesimals are not yet planets. They are more akin to small asteroids or comets, perhaps a few kilometers across. They are the first significant clumps to survive the initial chaotic collisions and flatten into the disk. Their orbits are now far more stable, locked into the predominant direction of the disk's spin. The beauty of this process lies in its self-correcting nature. Any particle attempting to orbit outside this flat plane or against the prevailing direction of rotation would swiftly encounter numerous other particles moving in the correct manner, leading to collisions that would either force it into the common plane and direction or scatter it away from the system entirely. This natural selection, this gentle weeding out of discordant motion, ensures the remarkable uniformity we observe in our solar system today. It's a truly elegant solution, a testament to the universe's inherent drive towards order. The protostar continues to grow, drawing in material not just from the immediate vicinity of the disk, but also from the outermost reaches of the original nebula. As its mass increases, so does its gravitational influence, further stabilizing the protoplanetary disk and cementing its flat rotating structure. The spin imparted to the protostar by the infalling material is a crucial detail. Imagine the entire disk as a colossal flywheel slowly turning. As material from this flywheel spirals inward and lands on the central protostar, it transfers its rotational energy, causing the protostar to begin its own majestic, leisurely spin. This ensures that the star, when it finally ignites, will also be rotating in the same harmonious direction as its planetary offspring. It is a cosmic dance where every participant, from the central star to the outermost dust particle, is perfectly synchronized, moving to the same ancient unspoken rhythm. The very act of formation imbues the system with this remarkable unified spin, a silent testament to its shared origin and destiny. This process, though vast in scale and time, is rooted in simple, elegant physics. It is the story of how scattered chaos, given enough time and the subtle guiding hand of gravity and angular momentum, can transform into breathtaking order. It's a lullaby of creation, a cosmic whisper of beginnings, reminding us that even the most complex and beautiful structures in the universe often arise from the most humble and chaotic origins. As the protostar at the heart of our nascent solar system continued its slow, patient maturation, drawing ever more material into its gravitational embrace, the magnificent disk of gas and dust swirling around it also began its next profound transformation. No longer just a chaotic swirl of colliding particles, this protoplanetary disk, now beautifully flattened and unified in its spin, entered a new phase of creation. Imagine a vast, luminous cosmic river, its currents flowing with exquisite precision. Yet within its gentle flow, new smaller eddies and whirlpools begin to form. This is the stage of gentle clumping of material within the disk itself. Particles once scattered and seemingly independent found themselves drawn to one another by their own tiny cumulative gravitational whispers. These were not the violent energetic impacts of the earlier chaotic phase. Rather, they were softer, more deliberate gatherings like snowflakes gently accumulating to form a drift, slowly, steadily adding to their mass. This ongoing process of accretion of particles, patiently clinging together, held within it the breathtaking possibility of different cosmic destinies. If by some cosmic grace, enough material had gently clumped together in one particularly dense region of the disk, accumulating a truly immense amount of mass, it might have eventually ignited into another star. This would have transformed our solitary sun into part of a binary or even a multi-star system, a celestial family with two or more luminous hearts dancing in a grand, intricate embrace. Imagine the skies of such a world, lit by the twin glows of two suns, casting an ever-shifting tapestry of light and shadow. However, in our particular cosmic story, the sun, in its burgeoning majesty, became the dominant gravitational force, eventually drawing in the lion's share of the available material. Thus, these less massive clumps, unable to reach the critical mass required for stellar ignition, were instead destined for a different, yet equally profound fate. They would eventually coalesce into planets. It was a slower, more deliberate process, as countless smaller particles and planetesimals, the cosmic building blocks, continued their gentle collisions and mergers, gradually growing in size until they became the majestic spherical worlds we know today. And as these magnificent planets began to take shape, emerging from the swirling depths of the protoplanetary disk, a remarkable echo of the original formation process began to unfold around them. Each fledgling planet, now a substantial gravitational entity in its own right, started to gather its own miniature swirling disk of leftover gas and dust. These were the planetary disks, smaller intimate versions of the grand protoplanetary disk that birthed the planets themselves. Just as the larger disk influenced the spin of the sun, these nascent planetary disks, with their own gentle consistent rotation, began to impart their angular momentum to their planetary parents. This intimate dance caused the planet to rotate in the same direction as the disk was spinning, a perfect cosmic synchronization. And within these smaller planetary disks, the same patient process of clumping and accretion occurred once more. As material continued to gently gather and coalesce, these smaller clumps over vast stretches of time eventually formed the moons that gracefully orbit our planets, each a tiny world, dancing in attendance around its larger companion. It is a stunning demonstration of a fractal-like pattern in the universe, where the grand design of the solar system's formation is mirrored and repeated on smaller, more localized scales. This mesmerizing process of material clumping of cosmic building blocks patiently gathering is not merely a theoretical construct confined to the distant past. It is a dynamic process that we can, in a truly awe-inspiring way, observe even today, right within our own solar system. The magnificent planet Saturn, with its unparalleled mighty disk of rings, serves as a living laboratory for this very phenomenon. During its incredible mission, the Cassini spacecraft, a silent observer from Earth, was able to peer deep into Saturn's glorious ring system and spot something truly extraordinary: tiny moonlets forming within the rings themselves. These ephemeral nascent moons were seen to emerge as the countless particles of ice and rock within Saturn's rings, gently clumped together, drawn by various subtle gravitational interactions. It was like witnessing the universe in the act of creation, a fleeting glimpse of the very processes that once sculpted our own worlds. Some of these delicate moonlets, perhaps still too fragile, fell apart soon after their brief formation, unable to withstand the subtle stresses and disruptions within the dynamic ring system. And indeed, it is almost certain that similar ephemeral clumps, these early cosmic experiments in planet formation, also formed and dissolved repeatedly in the chaotic early days of our own solar system. Long before the stable planets we know today took permanent shape, but remarkably, some of these brave little moonlets within Saturn's rings lasted until the very end of Cassini's mission, enduring the relentless cosmic dance. And perhaps, just perhaps, if the conditions remain just right, some of them will eventually endure and grow, forming into very tiny, stable moons. One day, much like some of the other shepherd moons that already exist, which have over eons gently carved clear, distinct paths within the rings themselves, like invisible cosmic gardeners tending to a grand design. Now, as we contemplate this wondrous order, it is important to acknowledge that the orbital plane of our solar system, while remarkably flat, isn't perfectly geometrically flat. There are subtle variations, gentle undulations. Some planets, in their long, graceful cosmic journeys, exhibit slight variations of a few degrees from the absolute average plane. It's not a rigid, unyielding sheet, but rather a vast, gently undulating cosmic tapestry. However, these minor deviations do not diminish the overarching sense of order. They merely add a touch of natural beauty, a subtle imperfection that makes the pattern even more captivating. It definitely is a profound pattern, a testament to the powerful self-organizing forces that shaped our celestial home. There is something almost profoundly beautiful in this cosmic irony, how in the grand theater of nature, something that begins as utterly chaotic, a swirling turbulent cloud of gas and dust, will, given enough time and the gentle guidance of fundamental laws, eventually form something so remarkably calm, orderly, and enduring. It's a journey from discord to harmony, from randomness to exquisite design. As material within the solar system, like wandering asteroids and comets, continues its eons-long journey, occasionally finding new homes. By impacting the planets, the intensity and frequency of these cosmic collisions have dramatically lessened over time. We can already observe a profound reduction in the amount of such impacts that have taken place since the solar system's tumultuous youth. The evidence for this can be read in the very scars of celestial history by measuring the age of craters on exposed celestial objects like our moon and other ancient airless bodies. These craters, like silent witnesses, tell a compelling story. From these ancient clues, these pockmarks on the face of time, we can clearly see that all the planets were subjected to heavy bombardment from countless asteroids and smaller planetesimals. The planet dececimals during that early, incredibly chaotic beginning. Imagine a cosmic shooting gallery, a relentless barrage of rocky and icy fragments. However, the amount of these devastating collisions gradually and steadily reduced as more and more material found its place, either coalescing into larger bodies or being swept away, until what we see today is the relatively calm and orderly solar system we inhabit, a haven of comparative peace after a tumultuous birth. This remarkable transformation from a swirling chaotic nebula to a structured harmonious solar system is a quintessential example of a type of natural phenomenon known as emergent structures through self-organization. It's a concept that resonates deeply with the universe's inherent artistry. In essence, emergent structures are patterns or order that arise spontaneously from the interactions of many simpler components without any central planning or external direction. Imagine a flock of birds, each bird following a few simple rules about its neighbor, yet collectively forming breathtaking swirling patterns in the sky. Other self-organizing emergent structures in nature are strongly comparable to this cosmic process, offering intriguing parallels. For instance, consider the intricate, powerful development of hurricanes. From seemingly random atmospheric disturbances, complex, deeply attractive, and highly organized spiral patterns emerge, driven by fundamental physical forces. So in the broadest sense, emergent structures are basically where pure randomness can give rise to complex and deeply attractive, orderly structures. It is a profound testament to the universe's capacity for self-assembly, its inherent ability to weave intricate tapestries from disparate threads. We observe this mesmerizing process of self-organizing taking place across countless scales in space, from the graceful flat orbital planes in planetary systems like our own, to the larger, more intricate arrangements within entire solar systems, and even extending to the colossal, swirling grandeur of galaxies themselves, where billions of stars coalesce into magnificent spiral or elliptical forms. It's a recurring theme, a cosmic symphony played out on every conceivable stage. As a gentle side note, a quiet whisper from the deeper cosmic realms, we also see this principle of self-organization at play in the very formation of individual stars and planets themselves, from the initial collapse of gas clouds to the accretion of solid bodies. And stretching our minds to the grandest possible scale, this principle is to a truly large extent even evident in the very origins of the universe itself, in the moments immediately following the Big Bang. From an unimaginably hot, dense, and uniform state structure began to emerge, forming the first subatomic particles, then atoms, then galaxies, and eventually life. Given all this compelling evidence, all these recurring patterns observed across the cosmic canvas, we are led to a humble yet profound assumption that similar processes must have formed other star systems scattered throughout the universe. And indeed, with the ever-advancing gaze of our telescopes, we have already been able to observe massive planets orbiting other stars along remarkably similar planes, providing tantalizing, confirming whispers of this universal principle at work. It is a quiet reassurance that we are not alone in our cosmic order, that the rules of creation are universal and elegantly consistent. As we gently reflect upon the profound journey from a swirling, turbulent nebula to the beautifully structured and harmonious solar system we inhabit, our minds are quietly drawn to a grand overarching principle that governs much of the universe's inherent artistry. This remarkable transformation, this elegant progression from cosmic chaos to a state of profound order, is a quintessential illustration of what is scientifically, yet quite poetically described as emergent structures through self-organization. It's a concept that resonates deeply with the universe's intrinsic drive to create complexity from simplicity, its capacity to sculpt intricate patterns without any direct external intervention. Imagine for a moment the seemingly random dance of countless individual water molecules. Yet when enough of them gather under specific conditions, they spontaneously form the intricate, symmetrical beauty of a snowflake. No two are exactly alike, yet all share a fundamental underlying design. At its heart, self-organization is a powerful, almost mystical process where patterns or order arise spontaneously from the intricate interactions of many simpler components without any need for central planning or an external guiding hand. Consider the breathtaking spectacle of a flock of starlings at dusk swirling and shifting in mesmerizing patterns against the twilight sky. Each individual bird follows only a few simple local rules about its immediate neighbors, maintain a certain distance, match their speed, and move towards the center of the group. Yet when these simple interactions are multiplied across thousands of birds, the collective behavior gives rise to fluid, complex, and utterly beautiful aerial ballets. No single bird is dictating the grand design. The pattern emerges from the collective, decentralized intelligence of the group. This is the essence of self-organization. The whole becomes far greater and far more organized than the sum of its individual parts. Other self-organizing emergent structures in nature offer equally intriguing parallels to this cosmic process, providing tangible, relatable insights into the universe's profound capacity for order. For instance, consider the intricate and immensely powerful development of hurricanes. These colossal weather systems often begin as seemingly random atmospheric disturbances, perhaps a subtle shift in temperature or pressure over warm ocean waters. Yet as these initial, almost imperceptible fluctuations interact and amplify each other, a complex, deeply attractive, and highly organized spiral pattern begins to emerge. The winds gather into a swirling vortex, driven by fundamental physical forces, creating a distinct eye at the center, a calm core within a violent storm. No external blueprint guides its formation. The hurricane self-organizes from the interplay of heat, moisture, and the Earth's rotation. The very forces that bring about destruction also craft a structure of profound, albeit fearsome beauty. So in the broadest and most gentle sense, emergent structures are basically where pure, often seemingly formless randomness can give rise to complex and deeply attractive orderly structures. It is a profound testament to the universe's inherent capacity for self-assembly, its innate ability to weave intricate, self-sustaining tapestries from disparate and initially uncoordinated threads. We observe this mesmerizing process of self-organizing, taking place across countless scales within the boundless expanse of space. Think of the graceful, almost impossibly flat orbital planes in planetary systems like our own, where billions of individual particles coalesced into distinct, synchronized worlds. This order arose not from external decree, but from the internal dynamics of the system. This principle extends to the larger, more intricate arrangements within entire solar systems where stars and their planets maintain their celestial dance over eons. And it stretches further still, encompassing the colossal swirling grandeur of galaxies themselves, where billions upon billions of individual stars coalesce into magnificent spiral arms or smooth elliptical forms, all governed by the relentless unifying embrace of gravity. It is a recurring theme, a grand cosmic symphony played out on every conceivable stage, from the smallest gathering of dust to the largest clusters of galaxies. Allow me to offer a gentle side note, a quiet whisper from the deeper cosmic realms hinting at the universality of this principle. We also see this concept of self-organization at profound play in the very formation of individual stars and planets themselves. From the initial gravitational collapse of vast, diffuse gas clouds, a seemingly formless expanse, to the painstaking particle-by-particle accretion of solid bodies within the protoplanetary disks. The process of self-organization is a continuous guiding force, and stretching our minds to the grandest possible scale to the very fabric of existence, this principle is to a truly large extent even profoundly evident in the very origins of the universe itself, in the moments immediately following the Big Bang. From an unimaginably hot, dense, and uniform state, a state of ultimate simplicity structure began to emerge. The first subatomic particles coalesced, then atoms, then the first stars and galaxies, all driven by fundamental forces interacting in self-organizing ways. It is a testament to the universe's fundamental architecture, a quiet, reassuring hum that echoes through all of creation. Given all this compelling evidence, all these recurring patterns observed across the cosmic canvas, from the micro to the macro, from the fleeting to the eternal, we are gently led to a humble yet profoundly significant assumption that similar processes must have formed other star systems scattered throughout the universe. It would be a disservice to the elegance of cosmic laws to assume that our own formation was a unique, isolated anomaly. Instead, the whispers of universal principles suggest that wherever the conditions are ripe, where vast clouds of gas and dust exist, where gravity can begin its patient work, the same self-organizing dance of flattening disks and synchronized orbits will likely unfold. And indeed, with the ever-advancing keen gaze of our most powerful telescopes, we are now able to glimpse these distant echoes of creation. We have, with astonishing clarity, been able to observe massive planets orbiting other stars along remarkably similar planes, providing tantalizing confirming whispers of this universal principle at work. These exoplanetary systems, shimmering points of light in the vast cosmic ocean, are like distant mirrors reflecting the very story of our own beginnings. It is a quiet reassurance that we are not alone in our cosmic order, that the rules of creation are universal and elegantly consistent, woven into the very fabric of space-time itself. The humbling vastness of the universe, punctuated by these recurring patterns, invites a unique blend of awe and introspection. It suggests that while each star system, each galaxy possesses its own unique cosmic biography, the underlying narrative, the fundamental principles of its genesis, are shared across the immeasurable expanse. This cosmic commonality fosters a sense of gentle connection, a quiet understanding that the same physical laws that govern the gentle sway of a tree on Earth are also orchestrating the grand ballet of galaxies colliding billions of light-years away. This shared script of creation lends a subtle yet profound beauty to the cosmos, turning abstract scientific concepts into a shared universal poetry. The gentle reassurance that we are part of a grand elegant system, a self-organizing masterpiece, is a soothing thought as we prepare for slumber. It dissolves the anxieties of random chaos and replaces them with the quiet certainty of underlying order. Our existence, the very configuration of our planetary home, is not a fluke, but the logical, beautiful outcome of processes that are inherent to the universe itself. We are not accidental inhabitants of a formless void, but rather intricate threads in a cosmic tapestry woven with invisible, intelligent design, a design that emerges from the simplest interactions. This interconnectedness of all things, from the smallest, most elusive particle to the largest, most majestic galaxy, is a profound concept to embrace. The same gravitational pull that draws an apple to the Earth also holds distant stars in their galactic orbits. The same principles of energy dissipation that allowed our protoplanetary disk to flatten are at play in the formation of swirling gas clouds light-years away. It speaks to a universe that is a singular, unified entity, a cosmic symphony where every note, every instrument contributes to the overarching harmony. The beauty of the unknown, the mysteries that still beckon from the deepest corners of the cosmos, are not voids of understanding, but rather expansive spaces for unending wonder. They invite us to continue our gentle exploration, to keep asking questions, and to remain open to the quiet revelations that the universe consistently offers. The ongoing dance of gravity and matter forever shaping the cosmos is a lullaby of creation, a constant, soothing hum that resonates through the silence of space. It's a perpetual process of becoming where nothing is ever truly static. Yet everything moves with a profound sense of purpose and rhythm. The intricate tapestry of cosmic laws, weaving order from potential chaos, is a testament to the universe's innate ability to bring forth beauty from its own essence. It suggests that even in the seemingly empty vacuum, there is an underlying vitality, a restless hum that fuels creation. The universe is not a rigid fixed machine, but a dynamic, ever-evolving artwork, constantly refining itself. This chapter concludes with a gentle invitation to simply observe and wonder, to let go of the need for definitive answers for a moment, and instead to simply bask in the magnificent uncertainty, to contemplate the vastness, the order, and the enduring mystery. The knowledge that the cosmos is a self-organizing entity, always finding its way to balance and structure, is a deeply comforting thought. It implies a universe that is fundamentally stable, capable of enduring and recreating itself, constantly blossoming into new forms and new wonders. As we drift into sleep, let the image of a universe that creates its own harmony, that sculpts its own beauty from the raw materials of existence, fill your mind with peace. Think of how many other planetary systems might exist, each one a unique expression of these universal principles, yet each sharing the fundamental architectural signature of a flat spinning disk. Each one a tiny island of order within the vast, dark ocean of interstellar space. And each one, in its own way, tells a story of emergent order, a silent testament to the universe's incredible capacity for creation. We are part of this grand ongoing story, and our quiet contemplation of it is a beautiful act in itself. The universe does not impose order from the outside. It reveals it from within. It's like watching a crystal form molecule by molecule, assembling itself into a structure of astonishing perfection, or observing the intricate patterns that emerge in a sand dune, sculpted by the relentless yet simple forces of wind. These are not accidents, but the inevitable consequences of fundamental interactions playing out across time and space. And in this knowledge, there is a deep, quiet comfort, a sense of belonging to something far greater and more enduring than ourselves. This journey through the principles of self-organization invites us to see the world, and indeed the cosmos, through a new lens, one that appreciates the elegance of simplicity, leading to complexity of chaos, yielding to breathtaking order. It's a reminder that even when things seem most tumultuous, there might be an underlying unseen hand of cosmic law, guiding them towards a more stable, harmonious state. A gentle thought to carry into your dreams that the universe in its very essence is constantly organizing, always seeking its own beautiful balance. Let us now turn our gentle gaze towards a truly fascinating celestial neighbor, a giant in our own cosmic backyard, and ponder a question that has sparked many a curious mind. Perhaps even in childhood dreams, could Jupiter have been a star? I remember when I was much younger, I harbored a whimsical yet vivid dream of journeying to Jupiter, armed with a single match and somehow setting its vast hydrogen atmosphere ablaze, thus igniting a magnificent second star in our solar system. The thought was intoxicating, the idea of our night sky, suddenly graced by two luminous suns, a constant, gentle glow. There were, of course, several fundamental problems standing quietly in the way of executing such a grand plan, not least of which was the rather crucial fact that there is simply no free oxygen on Jupiter to ignite its abundant hydrogen. The reality of space in its elegant simplicity often humbles our wildest imaginings, but even with the practicalities gently set aside, that profound question lingers a quiet whisper in the cosmic winds. Could Jupiter have been a star had things unfolded a little differently in the universe's grand narrative? Is Jupiter, in essence, a failed star? And the answer, as with many of the universe's most intriguing questions, is a subtle and nuanced one, a gentle dance between yes and no. It is no in the sense that Jupiter is not something astronomers specifically categorize as a brown dwarf, which by its very definition is considered a failed star. Brown dwarfs occupy a fascinating middle ground in the celestial spectrum. They are far more massive and significantly hotter than Jupiter. Yet they never quite achieve the critical mass and internal pressure required to sustain stable nuclear fusion in their cores. The very process that allows true stars like our Sun to shine brightly for billions of years. These cosmic in-betweens generally form independently of other stars, perhaps within the cooler, denser pockets of a vast molecular cloud, where other more successful stars are also being born. They are like solitary wanderers, never quite reaching the brilliance of their stellar kin. To truly appreciate the subtle distinctions, let us watch in our mind's eye a computer simulation of a molecular cloud, collapsing and forming stars. Imagine a vast, swirling, ethereal cloud of gas and dust so immense it stretches light years across, slowly, inexorably beginning to contract under its own gentle gravitational embrace. As this colossal cloud begins to pull inward, various denser pockets within it start to collapse faster, forming the nascent seeds of future stars. Within this dynamic, ever-changing environment, certain objects perhaps caught in a cosmic crosscurrent or receiving an unexpected gravitational nudge are flung away from the cloud before they have had the opportunity to acquire enough mass to become true incandescent stars. These unfortunate cosmic exiles forever adrift in the interstellar void are the ones most likely to become brown dwarfs. They are the stars that never quite made it, forever glowing faintly, cooling slowly, never achieving the brilliance of their successful siblings. On the other hand, within the same simulation, you observe other objects that by cosmic fortune continue their patient accumulation. These celestial entities persist in their relentless quest to pull in more and more mass from the cloud. Their gravitational appetites are insatiable, their growth unchecked. These fortunate accumulators are the ones destined to become main sequence stars. Stars like our own Sun, which will spend billions of years burning hydrogen in their cores, illuminating their surroundings with a steady, reliable light. If we were to gently zoom in on a star forming within this cosmic nursery, a breathtaking sight would unfold before our inner eye. You would clearly see that a delicate yet substantial disk of gas and dust from the molecular cloud has formed around it. This swirling flattened structure, a cosmic potter's wheel, is what we call a protoplanetary disk. And it is within this very disk, this fertile cosmic ground, that planets eventually begin to take shape, patiently emerging from the surrounding chaos. You can almost see the making of planets starting to blob together over time like tiny droplets of water, slowly merging on a window pane, gradually growing into larger and larger spheres. It is from this very type of protoplanetary disk that we believe Jupiter came from, just like all the other planets in our solar system. Jupiter wasn't an independent cosmic wanderer destined to become a brown dwarf. It was an integral part of our Sun's own birth, a product of the very same swirling material that created our luminous star. But this begs another fascinating question that often floats through the mind. Aren't there loads of star systems out there with more than one star systems where 2 or even 3 suns dance in a complex celestial embrace? That is absolutely true. Many multiple star systems exist, showcasing a far more intricate gravitational ballet than our own. These systems may have formed when 2 or more stars, perhaps born close together within the same stellar nursery, gracefully met up and stayed together, their mutual gravity binding them in a perpetual multi-star embrace, much like these magnificent examples we observe across the cosmos. However, in the unfolding drama of our own solar system's genesis, our nascent Sun proved to be remarkably greedy for mass during its development. It possessed an insatiable gravitational appetite, drawing in the vast majority of the available material from the surrounding molecular cloud itself. To give you a humbling comparison, consider this astonishing fact. Our Sun alone contains a staggering 99.8% of the total mass of the solar system. Now contrast that with Jupiter, the king of our planets, which, despite its immense size, contains a mere 0.1% of the solar system's total mass. This vast disparity highlights the profound dominance of our Sun. Jupiter's fundamental problem, if we can call it that, was not a lack of ambition, but rather its unfortunate cosmic birthplace. It formed within the Sun's own protoplanetary disk. And tragically, for Jupiter's stellar aspirations, the material in that disk, the very cosmic soup from which it was trying to grow, was exhausted before it had a chance to get massive enough itself to ignite nuclear fusion and become a true star. It was simply outcompeted by its colossal parent. So going back to our original gently posed question, yes, in a very specific and humble sense, Jupiter is a failed star in that it failed to become a star. But, and this is the crucial nuance, that same cosmic failure also happened with all the other planets in our solar system. Every single world orbiting our Sun, from the smallest asteroid to the largest gas giant, is by this same definition a failed star. They all emerged from the same disk, and they all lacked the immense mass required to ignite their own internal furnaces. This perspective gently shifts our understanding. It's not that Jupiter is uniquely special in its failure, but rather that its immense size merely brings this universal planetary destiny into sharper focus. It reminds us that being a planet is a distinct and equally miraculous cosmic path, one that leads to the diverse and vibrant worlds we so dearly cherish. The universe, in its infinite wisdom, assigns different roles, and Jupiter, as a magnificent planet, plays its role with unparalleled grandeur. The concept of a brown dwarf, that fascinating, failed star, opens a window to the vast spectrum of celestial objects that exist beyond our immediate understanding. They glow with a dull, persistent heat, slowly fading over eons, never quite achieving the brilliance of a true star. Their very existence reminds us that the line between a star and a planet isn't always sharp and distinct, but rather a gradual continuum, a spectrum of possibilities dictated by the sheer amount of matter that can be gathered in one place. Jupiter, in its quiet majesty, sits comfortably on the planetary side of that line, a testament to the fact that even without nuclear fire in its core, it remains a dominant and awe-inspiring force in our solar system. The delicate balance of gravity and mass, the finite availability of material in a protoplanetary disk. These are the subtle cosmic arbiters that decide the fate of nascent celestial bodies. It's a game of cosmic chance and physics played out on an unimaginable scale, where some accumulate enough to shine independently, while others are destined to become companions, reflecting the light of their dominant star. This shared origin story, this intricate dance of accretion within the same swirling disk, binds all the planets, including Jupiter, to our Sun in an unbreakable cosmic family bond. The idea of a multi-star system, while not our reality, offers a beautiful glimpse into the universe's boundless creativity. Imagine the shifting shadows, the double sunsets, the unique ecosystems that might arise under the embrace of two or more suns. It is a reminder that our own solar system, in its singular star simplicity, is just one of countless variations on a cosmic theme, each one a unique masterpiece born from the same fundamental laws. Our Sun's greed for mass was not a flaw, but a defining characteristic that led to the specific harmonious arrangement we observe today, a system dominated by a single powerful star with its planets orbiting in a precise, elegant dance. This contemplation of Jupiter, the largest of our planetary siblings, as a failed star, truly emphasizes the incredible mass of our Sun. It puts into perspective just how much matter is packed into that central ball of incandescent gas, and how little is left over for everything else, even the behemoth Jupiter. The very fact that Jupiter, with all its grandeur, only accounts for 0.1% of the solar system's mass, compared to the Sun's 99.8%, is a humbling thought. It speaks to the Sun's overwhelming gravitational pull, its ability to dominate and sculpt its cosmic surroundings. This immense mass is not just for show. It is the fundamental reason why our solar system functions as it does, why planets remain in stable orbits, and why life on Earth is bathed in a steady, life-giving glow. As we conclude this reflection on Jupiter, let the idea of a failed star soften into the understanding of a successful planet. Jupiter, in its role as a giant protector, a cosmic vacuum cleaner diverting countless asteroids and comets away from the inner solar system, plays a vital role in the delicate balance of our cosmic home. Its immense gravity, even without stellar fire, is a powerful force for order and stability. So in this gentle light, Jupiter is not a failure, but a magnificent success, perfectly fulfilling its planetary destiny within the grand design of our solar system. Let this thought drift into your dreams, a quiet appreciation for the specific beautiful path our cosmic neighborhood has taken. Now let us gently shift our gaze from the grand story of formation to a question that often arises when we consider the immense scale of our cosmic home. Ever wondered where the boundary of our solar system truly lies? Is it merely up until the orbit of Pluto, that distant, beloved dwarf planet? Or does it stretch further, perhaps encompassing the icy expanse of the Kuiper Belt, a vast ring of leftover material beyond Neptune? Or does it extend even further still into realms almost beyond our current imaginings? You may have heard in hushed tones of cosmic achievement that the Voyager spacecrafts have already left the solar system, their current positions placing them well beyond the familiar icy confines of Pluto's orbit. But in the grand cosmic reality, to simply say they have left the solar system is not entirely true. It is a simplification, a gentle shorthand for a far more intricate and expansive truth. So how then do we define the true edge of a solar system, if not by the familiar orbits of its planets? And following on from that, how truly big can solar systems get across the vast tapestry of the universe? Let us look first, with quiet admiration, at where the Voyagers are currently situated and gently explore why some might confidently assert that they have already left our solar system. It is nothing short of astonishing that these twin robotic explorers, the Voyagers, which were launched way back in 1977, a time when many of us were not even a thought, are still remarkably operational today, tirelessly sending back whispers from the deep. Though it must be noted, they are operating at somewhat reduced capacities, their once robust array of instruments now trimmed to conserve precious energy. Their remarkable longevity and continued journey are powered by ingeniously designed radioisotope thermoelectric generators, often affectionately called RTGs. These miniature cosmic powerhouses are a marvel of engineering, truly exceptional at providing consistent power without any reliance on the sun's diminishing light at such extreme distances. They generate electricity by converting the heat released from the decay of radioactive material directly into electrical current, a steady, unwavering pulse of energy. However, with every passing year, with every gentle turn of the cosmic clock, the radioactive material within these generators subtly degrades slowly but inexorably, producing less power. It's like a quiet internal flame gradually dimming over eons. The Voyagers are currently operating with approximately half the power they had when they first embarked on their epic journey almost 5 decades ago. This gradual decline in power has necessitated a thoughtful strategic decision. A few of their less critical instruments have had to be gently turned off, conserving energy for the vital few that continue their silent vigil. What these remarkable, enduring Voyagers are currently monitoring with their remaining active instruments is the magnetic field environment of deep space and its intricate, subtle interactions with the solar wind. Imagine our sun a colossal fiery heart constantly exhaling a stream of charged particles. The solar wind, that rushes outwards, carrying the sun's magnetic field far into space, forming a vast protective bubble around our solar system. Of particular and profound interest to the dedicated scientists who patiently listen to the Voyager's faint signals is a crucial boundary, a cosmic frontier where the sun's magnetic field and its relentless solar wind are finally gently overcome by the interstellar wind. This interstellar wind is a faint ethereal current of gas and dust that flows through our Milky Way galaxy, a gentle breeze in the vastness between star systems. This pivotal boundary, this cosmic shoreline where our sun's domain finally yields to the broader galactic currents, is known as the heliopause. It is a place of profound transition, a cosmic threshold. Scientists meticulously analyzing the data whispered back across billions of miles believe that Voyager 1 gently crossed this boundary in 2012, stepping for the first time into the true interstellar space. Its twin Voyager 2 followed suit in 2018, making both of them the only human-made spacecraft to ever make this historic leap, truly venturing beyond the immediate influence of our sun's protective bubble. What they found out on their arduous silent journey, and what they continue to reveal to us, is that this boundary, the heliopause, is not a perfectly spherical ball neatly encompassing the sun. Oh no, the cosmos is rarely so geometrically simple. Instead, it's rather bubbly and asymmetrical, a testament to the complex and dynamic interplay of forces in the interstellar medium. And much like planets facing into the sun with their own magnetic fields, subtly trailing behind them because of the constant interaction with the solar wind, imagine a cosmic flag fluttering in a breeze. The sun's own magnetic field also trails behind it, gently pushed and shaped by the interstellar wind. It forms a vast, teardrop-shaped cocoon with a long flowing tail stretching far behind it as it travels through the galaxy. As our entire solar system, a magnificent cosmic vessel, gracefully orbits the center of the Milky Way galaxy. It embarks on an incredibly swift journey, traveling at an astonishing speed of over 800,000 kilometers per hour. Imagine the sheer momentum, the colossal scale of this galactic dance. As it moves relentlessly through the vast expanse of the galaxy, our solar system simultaneously passes through what is known as the interstellar medium, the incredibly thin but omnipresent gas and dust that permeates the space between stars. It does so at a relative speed of approximately 80,000 kilometers per hour. This constant subtle motion creates a kind of wind effect on the magnetic field of the sun, much like a giant invisible hand gently shaping it. This continuous interstellar breeze leaves a vast shimmering tail in the interstellar wind's wake, a long ethereal streamer of solar influence stretching far behind our cosmic home. But as fantastic and inspiring as the Voyager mission is, with its pioneering journey into the interstellar depths, it's crucial to understand a subtle yet profound distinction. Reaching interstellar space is not the same as reaching the absolute edge of the solar system. While the heliopause marks the boundary where the sun's wind and magnetic field are overcome by the interstellar medium, it does not mark the ultimate reach of the sun's most fundamental influence, its gravity. The true all-encompassing edge of our solar system is defined not by winds or magnetic fields, but by the subtle yet incredibly persistent reach of gravitational influences. This ultimate boundary, this cosmic horizon, is known as the Hill sphere, though it should be gently noted that much like the heliopause, this is not truly a perfect geometrically defined sphere either. Its shape, as we will softly explore, is sculpted by the complex gravitational landscape of our galactic neighborhood. I'll come to that intriguing asymmetry in a bit. For now, let us softly define what a Hill sphere truly means. A Hill sphere is the cosmic bubble, the specific region around an object, where the gravitational pull of that particular object gently overcomes the gravitational pull of anything else in its immediate vicinity. It's like a personal gravitational embrace, a zone of undisputed dominance. For instance, our moon orbits the Earth because it is comfortably within the Earth's Hill sphere. It is close enough that the Earth's gravitational exertion on the Moon, its constant gentle tug, overwhelmingly dominates the more distant, weaker pull of the Sun. Similarly, any satellites that orbit the Moon itself are nestled safely within the Moon's hillsphere, where the Moon's gravity at that specific distance asserts a greater pull than that of either the Earth or the Sun. And extending this grand principle to our cosmic home, everything that faithfully orbits the Sun, every planet, every asteroid, every comet, is thus within the Sun's hill sphere, where the Sun's immense unwavering gravity comfortably overcomes the much fainter, more distant gravitational whispers of nearby stars. This, then, is the true ultimate gravitational boundary of the solar system. It's not about where the solar wind ends, but where the Sun's power to hold things in orbit finally gently gives way to the influence of other stars. The Voyager missions have truly redefined our understanding of the solar system's environment. They have taught us that the boundaries are not as clean-cut or simple as we once imagined. The heliopause itself, that bubbly dynamic barrier, is a testament to the constant interaction between our Sun and the galaxy it moves through. It's like a ship sailing through a cosmic ocean, constantly pushing against currents and creating its own wake. This dynamic boundary, constantly shifting and adapting, reminds us that space is far from empty and static. It is a vibrant living medium full of forces and interactions that shape everything within it. The very fact that these probes launched almost half a century ago are still operational is a quiet testament to human ingenuity and perseverance. Their faint signals, taking hours to reach us across the vast distances, are precious whispers from the edge of our understanding. Each bit of data they send back refines our mental map of the solar system, pushing the boundaries of what we thought we knew. They are our silent scouts, exploring the ultimate frontiers of our home, sending back dispatches from a realm no human has ever seen. The journey of the solar system around the galactic center is itself a powerful reminder of cosmic motion. We are not stationary. Our entire neighborhood is hurtling through space at incredible speeds, pulled by the invisible hand of the Milky Way's supermassive black hole. This motion, though imperceptible to us on Earth, is what creates the interstellar wind effect, shaping the heliopause and forming the Sun's magnetic tail. It's a dance on a truly grand scale, one that continually reshapes our cosmic bubble. So while the Voyagers have indeed achieved the remarkable feat of entering interstellar space, they haven't yet escaped the Sun's gravitational grasp. They are still bound to it, albeit tenuously, for many more millennia. Their journey, therefore, continues to be a part of our solar system's story, a silent, ongoing exploration of its outermost gravitational reaches. This distinction is subtle, but it's important for understanding the true scale and definition of our cosmic home. The heliopause is a barrier of winds and magnetic fields, but the hill sphere is a prison of gravity much larger and more encompassing. We are only just beginning to truly map the vast, uncharted territories of this ultimate boundary. Now let's delve a little deeper into that true ultimate boundary of our solar system, the hill sphere, and explore its fascinating, often asymmetrical nature. This isn't just a theoretical concept. It's a testament to the pervasive, subtle influence of gravity that stretches far beyond the reach of solar winds and magnetic fields. We've established that a hill sphere defines the region where an object's gravitational pull dominates over all others. For our solar system, this means where the Sun's gravity reigns supreme, holding everything in its enduring celestial embrace. However, when we gently peer at our local neighborhood of stars, the picture becomes more intricate, more nuanced. We find that these celestial neighbors are unevenly distributed around us. They're not placed at perfectly regular intervals like pearls on a string. Instead, they cluster and disperse, creating a varied gravitational landscape. This irregular distribution means that the Sun's hill sphere, its gravitational dominion, isn't really a perfect, geometrically flawless sphere. Oh no, the cosmos rarely adheres to such rigid simplicity. Instead, it's shaped like an invisible, slightly lopsided bubble, stretched and squeezed, by the subtle gravitational whispers of nearby stars. Take, for instance, the magnificent Alpha Centauri system. This stellar neighbor, a binary star system, is roughly 4 light-years away from us. That might sound like an immense distance, and indeed it is, but on a cosmic scale, it's remarkably close. What makes Alpha Centauri particularly influential in shaping our sun's Hill sphere is that it contains 2 sun-like stars. Imagine 2 powerful gravitational giants locked in their own close dance, their combined mass significantly greater than that of our solitary sun. Because of this dual potent gravitational influence, Alpha Centauri's total gravitational pull will be greater than the sun's in that particular direction. This means it exerts a stronger tug gently but relentlessly, pushing the boundary of that part of the Hill sphere closer to the sun. It's like having a stronger magnet nearby, subtly distorting the magnetic field lines of a weaker one. Our sun's gravitational reach is slightly curtailed, nudged inward by the powerful embrace of its stellar neighbors. On the other hand, if we cast our gaze in the opposite direction towards a star like Barnard's star, the gravitational landscape shifts. Barnard's star is a red dwarf star significantly less massive and cooler than our sun, and it resides about 6 light-years away. Being further away and far less massive, its gravitational influence on our solar system is considerably weaker. Consequently, the sun's gravitational influence would stretch much further in that direction. Imagine a cosmic tug-of-war in the direction of Alpha Centauri. There's a strong opposing pull shortening our rope, but in the direction of Barnard's star, the opposing pull is much weaker, allowing our rope to extend much further. This interplay of gravitational forces from various neighboring stars means our Hill sphere is not a smooth, perfectly round bubble, but rather an irregular undulating boundary expanding and contracting, depending on the strength and proximity of its cosmic rivals. Even if an object is fortunate enough to be orbiting within the sun's Hill sphere near the boundary, its orbit is inherently very precarious. Imagine a delicate ballet dancer performing on the very edge of a stage where the slightest misstep could send them tumbling. At these extreme distances, the gravity of the sun here is incredibly weak, a mere whisper of the powerful force that binds Earth to its orbit. The object's orbital velocity would be very slow-moving at a glacial pace compared to the inner planets taking tens or even hundreds of thousands of years to complete a single circuit around the sun. This slow, tenuous grip means that the slightest perturbation from a passing star, even one many light-years away, or the collective gravitational whisper of the Milky Way's vast stellar population, might be enough to knock this object out of orbit entirely. It could send it hurtling into the vast, cold expanse of interstellar space, forever severed from the sun's gentle embrace. That's precisely why astronomers currently believe that the furthest objects can safely orbit the sun is up to a maximum distance of 1 light-year. Even though the sun's Hill sphere, its theoretical gravitational dominion, might stretch out for 2 to 3 light-years in some directions, the practical limit for stable long-term orbits is much closer. Beyond 1 light-year, the gravitational tug-of-war with other stars becomes too significant, making an object's long-term allegiance to our sun highly uncertain. So what then is truly out there at these immense distances, beyond the familiar yet still very far confines of the Kuiper Belt? Is there anything at all, or is it merely an empty echoing void? Well, way beyond the Kuiper Belt, which is itself a vast icy asteroid belt extending beyond the orbit of Neptune, lies a truly immense and enigmatic region. This region, stretching from a distance of about 1 to 3 light-years from the sun, is known as the Oort cloud. It's a sphere, or perhaps more accurately, a thick shell of icy bodies, completely surrounding our solar system in every direction. We believe the Oort cloud is a sparsely populated region, a vast cosmic freezer containing billions or even trillions of icy bodies. These are not closely packed like the asteroids in the main belt. Instead, they are incredibly spread out, often many millions of kilometers apart. It's like a colossal diffuse cosmic halo, barely visible, yet immensely significant. We believe that this distant icy reservoir is where a small but profoundly important percentage of the long-period comets come from. These are the majestic ethereal wanderers that grace our inner solar system. Only rarely once every tens or even hundreds of thousands of years, embarking on truly elliptical orbits that carry them from the far reaches of the Oort cloud, spiraling inward towards the sun's warmth, only to return to their distant icy home. They are ancient messengers, bearing secrets from the very edges of our gravitational dominion. To give you some perspective about the truly mind-boggling size of this cloud, consider the indefatigable Voyager 1 spacecraft. Even after decades of relentless travel, it will take this intrepid explorer an astonishing 300 years just to reach the beginning of the Oort cloud. And once it arrives at this immense icy frontier, it could potentially take another 30,000 to 150,000 years to pass through it entirely. Astronomical distances, when truly contemplated, are simply mind-blowing, stretching the limits of our human comprehension. And remember, at these unfathomable distances, where the sun is a mere distant pinprick of light, we are still considered to be within our own solar system. The Hill sphere's gravitational embrace is that vast, that pervasive. It truly redefines what we perceive as home in the cosmic sense. The precarious nature of orbits near the Hill sphere's boundary is a poignant reminder of the delicate balance in the cosmos. Imagine a tightrope walker inching across a thin wire that stretches for miles with no safety net. The further they go, the more the wind pushes, the more their own subtle movements threaten to unbalance them. Similarly, an object at 1 light-year from the sun is barely holding on its loyalty to our star. Constantly tested by the faintest gravitational whispers from other stars, the gentle tides of the Milky Way, or even the cumulative effect of countless tiny unseen cosmic influences. This explains why, despite the theoretical reach of the Hill sphere, the actual observed stable orbits don't extend quite as far. The universe demands a certain stability for long-term residency, and beyond that, 1 light-year mark, the cosmic neighborhood simply gets too crowded, too gravitationally competitive for a steadfast, unchanging orbit. The Oort cloud itself, despite its immense scale and sparse population, is a treasure trove of cosmic history. These icy bodies, essentially pristine remnants from the very early days of our solar system's formation, have been preserved in the deep freeze of the outer reaches for billions of years. They are like time capsules, holding clues to the original composition of the protoplanetary disk before the inner planets fully formed. When a passing star or some subtle galactic tidal force gently nudges one of these icy fragments out of its distant stable orbit, it begins its long, slow, majestic fall towards the inner solar system, eventually warming up and developing the spectacular tail that we recognize as a comet. It is a slow, infrequent dance, but a beautiful one, connecting the innermost parts of our home to its furthest, most ancient frontiers. The sheer volume of space encompassed by the Oort cloud is almost impossible to grasp. If our solar system out to Neptune were the size of a dinner plate, the Oort cloud would be a vast, shimmering dome enclosing our entire house, perhaps even the block. It's not just a belt, but a truly three-dimensional sphere of icy potential surrounding us in every direction. And within this immense, silent realm, gravity still works its magic, holding these countless icy bodies, however tenuously, within the sun's grand gravitational family. The realization that our solar system is so much vaster than the orbits of its known planets is a humbling one. It expands our definition of home, stretching it out into distances that are difficult to comprehend. It suggests that there are still immense, largely unexplored regions right within our own cosmic backyard, waiting for future generations of spacecraft equipped with even more sensitive instruments to gently explore and map. The Voyagers, though, pioneers, have only just scratched the surface of this ultimate frontier. Their journey is a testament to the fact that even within what we thought we knew, there is still so much more to discover. So many more questions to gently ask of the cosmos. This contemplation of the Hill sphere and the Oort cloud leaves us with a profound sense of the universe's quiet immensity. It reminds us that gravity, though invisible, is the ultimate sculptor and bounder of celestial systems, its influence stretching far beyond the light of any star. It's a gentle thought to take into the quiet of the night, knowing that our sun, this familiar ball of light, still holds sway over a domain that is truly breathtakingly vast. And within that vastness, there are still countless secrets held by icy wanderers, patiently waiting for their moment to reveal themselves. Now that we've gently charted the vast, almost unimaginable reaches of our own solar system, peering into the gravitational embrace of the Hill sphere and the icy mystery of the Oort cloud, a new and perhaps even grander question naturally arises, a quiet whisper that echoes through the deepest chambers of cosmic contemplation. How big can solar systems truly get? It's a question that stretches the very fabric of our understanding, inviting us to imagine scale beyond our immediate grasp. While it's something we can't know for sure, as the universe holds countless secrets yet to be unveiled, we can certainly have an educated guess about what such an impossibly vast solar system might look like, based on the fundamental laws of physics that we observe. For the purpose of this particular thought experiment, to keep our minds gently anchored in stellar realities, we'll stick strictly to stars. To allow the inclusion of black holes, especially the supermassive ones at galactic centers, would be to immediately venture into realms that essentially encompass entire galaxies, blurring the lines between a single star system and a colossal stellar city. Our focus for now remains on the gravitational dominion of a solitary star, however grand it may be. The theoretical limit, as our current understanding of astrophysics suggests for the mass of a single star, is around 150 solar masses, meaning 150 times the mass of our own comforting sun. Beyond this colossal threshold, the internal pressures and radiation within such an enormous star become so intense that they would theoretically begin to tear the star apart, preventing it from forming or enduring in a stable state. It's like trying to fill a balloon with too much air. Eventually, it will burst. However, the universe in its boundless creativity often delights in testing the very boundaries of our theories. And indeed, there are some truly astounding stars out there that gently, yet decisively, test this theory. Consider the most massive star that we currently know of, a magnificent cosmic behemoth named R136A1. This star, defying our theoretical limits, is apparently a staggering 300 solar masses, twice the expected maximum. Its sheer scale is almost incomprehensible, a singular point of unimaginable power and brilliance. Now, a crucial detail to consider about R136A1 is that this titanic star does not exist in isolation. It resides in a very densely packed cluster of stars. Imagine a bustling cosmic metropolis where stars are born close together, their gravities constantly interacting and competing. So, although R136A1 is unbelievably massive, its gravity is in a perpetual silent competition with a lot of nearby stars. Every star in its vicinity is pulling and tugging, vying for gravitational influence. This intense gravitational competition from its neighbors reduces the size of its Hill sphere considerably. Its vast potential dominion is constantly being challenged, its gravitational reach effectively curtailed by the proximity and collective pull of its many stellar companions. It's like a king in a crowded court. His power is immense, but it's constrained by the presence of other powerful nobles. Now let us truly engage our imagination and embark upon a grand contemplative thought experiment. What if, by some extraordinary cosmic twist of fate, a star of this truly immense size, perhaps even a hypothetical 300 solar mass behemoth, was somehow ejected from its local cluster, gently propelled away from the dense gravitational embrace of its birthplace? Imagine it traveling further still, perhaps even launched clear of its local galaxy, drifting alone into the vast, silent emptiness between galaxies. In this profound isolation, it would find itself completely alone in space, with no other significant gravitational forces for many, many light years in any direction. The only other competing mass, the only other distant gravitational whisper, would be the colossal diffused pull of other galaxies themselves, stretching across billions of light years. In such an impossibly isolated scenario, where this colossal star exists as a solitary king in its own cosmic kingdom, with nothing immediately competing against it for gravitational dominance, its Hill sphere, its sphere of gravitational influence, would expand to truly mind-boggling proportions. Such a solar system driven purely by the immense unchallenged gravity of its central star could be hundreds to thousands of light years across. That's a distance that begins to approach, and in some interpretations even become comparable in size to a galaxy itself, depending on the precise distances involved and the mass of the star. Imagine a single star holding sway over a region of space that would normally contain millions or even billions of stars. It's a scale that redefines our very concept of a solar system. And now, let us push the boundaries of this thought experiment even further into a realm of pure cosmic hypothesis. Imagine a universe stripped down to its barest essentials, where only this one colossal star and a second much smaller object exist. No other stars, no other galaxies, just these two celestial companions, adrift in an otherwise empty cosmos. In such an impossibly vast, yet profoundly simple universe, that second, smaller object could be billions of light years away and still be irrevocably in orbit around the colossal star. This is a truly profound and perhaps counterintuitive realization. The reason is elegantly simple: gravity doesn't care how far away the objects are. It will still have an influence on them. Its pull, though diminishing with distance, never truly ceases. It merely weakens, stretching its invisible tendrils across unimaginable gulfs of space. In such a universe where only these two objects exist, eternally bound by the threads of gravity, the only escape for the second object from the gravitational pull of the larger object would be to have an infinite distance between the two. Only then, at the theoretical limit of infinite separation, would gravity's influence truly become zero. But of course, in any physically real universe, infinite distance isn't possible. Objects are always separated by a finite, albeit often immense number of light years. Therefore, in this hypothetical isolated two-body universe, the smaller object would be perpetually eternally bound in orbit, however slow, however vast, by the relentless, all-encompassing gravitational embrace of its larger companion. It's a testament to gravity's universal, unyielding reach, a force that connects everything everywhere always. So there we have it. Our own solar systems, with their familiar planets and vast Oort clouds, are already mind-bogglingly large, stretching our comprehension of scale. But the universe, in its infinite capacity for wonder and extreme conditions, reveals that under the right circumstances, they can be far, far larger. These hypothetical, impossibly vast solar systems, stretching hundreds or thousands of light years, are not just flights of fancy. They are logical extensions of the physical laws we observe, pushed to their ultimate theoretical limits. Still, the thought that sticks with me after researching all this, the quiet whisper that resonates most deeply, is that the universe truly is a fascinating, endlessly surprising, and profoundly beautiful place. It's a canvas of unimaginable scale, painted with the elegant brushstrokes of physics, where even the most extreme possibilities are rooted in the fundamental rules that govern all existence. The concept of a star exceeding the theoretical 150 solar mass limit, like R136A1, invites us to humbly acknowledge that our understanding, while robust, is always evolving. It reminds us that the universe is not obligated to conform perfectly to our models. Rather, our models must adapt to the universe's stunning reality. These cosmic anomalies are not problems, but rather invitations to deepen our knowledge, to refine our theories, and to expand our sense of what is possible. They are the universe's gentle nudges urging us to look beyond our current horizons. The idea of a star stripped away from its galactic context, floating in the interstellar void, highlights the pure, unadulterated power of gravity. In a dense cluster, gravity is a chaotic symphony of many instruments. But for an isolated star, gravity becomes a solo performance, its influence radiating outwards, unhindered and dominant. This purity of influence allows its hill sphere to swell to unimaginable sizes, defining a true personal kingdom in the cosmos. It's a reminder that distance, while weakening gravity, never truly breaks its hold, only stretches it. This stretching of gravity's influence across billions of light years in our hypothetical two-body universe is perhaps the most profound part of this thought experiment. It underscores the universal nature of gravity, its tireless and ceaseless work. It is the invisible thread that binds all matter from the smallest proton to the largest galaxy. It ensures that even across astronomical distances, objects are not truly isolated, but are perpetually linked, however faintly, by this fundamental force. This profound interconnectedness is a deeply comforting thought, suggesting that even in the vastness, nothing is truly alone. The implications for potential life in such unimaginably large solar systems are also fascinating to ponder. While the light from the central star would dim to a faint glow at thousands of light years, perhaps other forms of energy or geological processes could sustain life in such distant cold realms. It opens up new avenues for imagination, pushing beyond our familiar warm inner solar system. The universe, in its vastness, surely holds more possibilities than we can currently conceive. Ultimately, the question of how big is not just about numbers, but about perspective. It challenges us to expand our minds, to embrace the truly immense scale of creation. It is a humble reminder that our own solar system, while magnificent to us, is but a tiny, intricately ordered speck in a universe of endless possibilities. And in that humbling realization, there is a deep sense of wonder, a quiet awe that washes over us as we contemplate the boundless expanse of the cosmos. Let this thought linger as you drift into slumber, knowing that the universe holds secrets of scale and grandeur, far beyond our current dreams. Let us now embark upon a journey of scale, a quiet and imaginative exercise that helps us truly grasp the immense, often mind-boggling distances within our own celestial neighborhood. It's one thing to read numbers on a page, but quite another to truly feel the vastness. We'll revisit a classic thought experiment, a way to gently shrink the cosmos down to a more relatable size, allowing our minds to encompass the grand distances in a more tangible way. This time we will scale it down quite considerably, imagining our magnificent sun to be no larger than a tiny 1 millimeter grain of sand. Picture that minuscule luminous speck, almost invisible to the naked eye, yet still the mighty heart of our solar system. We'll place it gently right here, perhaps on the tip of your finger. With our sun now a mere 1 millimeter in diameter, like that tiny grain of sand, let us trace the paths of its planetary children. The closest planet to our sun, of course, is Mercury. In this scaled-down model, Mercury would be orbiting a surprising 4 centimeters away from our tiny sun. Imagine just a short, gentle hop, and there it is, a tiny pinprick of a world forever bound in a tight, swift dance around its miniature star. The next closest planet to our gentle sun is Venus, Earth's fiery sister. In our scaled model, Venus would be about 8 centimeters away. Just a little further doubling the distance from Mercury, and you'd find another tiny speck bathed in the sun's scaled-down warmth. Then we arrive at our own cherished home Earth, a vibrant living world. Earth would be approximately 10 centimeters away from our 1 millimeter sun. Think of it as just a short span, perhaps the length of your hand, a tiny fragile oasis in the vastness. Continuing our outward journey, the red planet Mars would be found about 16 centimeters away from our minuscule sun. A little more distance, a bit more coolness settling in. The next celestial body we'll gently mention here is Ceres, the largest dwarf planet residing within the main asteroid belt. Ceres would be a considerable 30 centimeters away from our Sun. Imagine stretching your arm out, and there, a small icy speck marking the beginning of a vast, scattered field of cosmic debris. Now we make a significant leap. The colossal gas giant Jupiter, the vacuum cleaner of our solar system, would be orbiting a remarkable 56 centimeters away from our tiny Sun. We are getting quite far away now, already needing to stretch our reach significantly. Then comes the majestic ringed planet Saturn. Saturn would be found a considerable 1 meter and 3 centimeters away from our 1 millimeter Sun. Imagine taking a few steps crossing the room, and there it is, another tiny distant world. Moving into the realm of the ice giants, we first encounter Uranus. This enormous tilted world would be a massive 2 meters and 6 centimeters away. A long walk indeed, needing to traverse the entire length of a small room. And finally, the last real planet in our solar system, the deep blue Neptune, would be a staggering 3 meters and 24 centimeters away from our tiny Sun. This is a considerable distance, requiring you to walk across several rooms, or perhaps a small garden to reach it. And then just beyond Neptune, we find Pluto, that beloved reclassified dwarf planet. Pluto would be approximately 4 meters and 22 centimeters away from our 1 millimeter Sun. This is truly the last familiar marker in our inner solar system at this scale. At this point, you might be gently wondering, what about the closest star, Alpha Centauri? Well, for that, you're going to have to imagine a truly epic journey. If our Sun was just that 1 millimeter grain of sand, Alpha Centauri, our closest stellar neighbor, would be a staggering 30 kilometers away. Imagine walking for hours or driving for a considerable distance just to find another equally tiny speck of light. This humbling comparison truly puts into perspective the immense emptiness between stars. Now let's try another mental exercise, scaling up our Sun to a size that might be a bit more tangible, something we can physically hold and feel. Let us imagine our Sun to be the size of an 11-inch football, a familiar object in our hands. This gives it a more substantial presence, a more immediate reality. And from this larger, more approachable starting point, let's see how vast the solar system becomes in comparison. We'll begin our walk stretching out towards Mercury. Right, we've walked about 38 feet away from where our football-sized Sun sits. That's how far Mercury would be in comparison. It's not a short distance, but certainly manageable. And if you were to look back, our tiny Mercury compared to the Sun would be only a tiny blip, a mere pinhead next to a football. Of course, at this scaled distance, it would still be incredibly hot, getting thoroughly roasted by the full blast of the Sun's scaled-down rays. It truly emphasizes the intensity of its proximity. Let's keep going, venturing towards Venus. All right, this is how far Venus would be from our football-sized Sun. If you were to look back just behind that distant car, or perhaps a specific landmark, that's where we started off. Venus again would be just a blip, almost as small as Mercury, but still a distinct entity. And again, it's also pretty hot at this scaled distance, as we're still relatively close to the Sun's tremendous scaled-down output. Now our own Earth is quite close to Venus. They often call it Venus's sister planet, though our fates diverged dramatically. And indeed, at this scale, Earth is about the same size as Venus, perhaps slightly bigger, a charming little blip in space. This, of course, is the perfect place for a planet to be in terms of its distance from the Sun to support life as far as we currently know. We live here, we're enjoying a nice day gently warmed by the Sun's life-giving rays. The conditions are just right. Let's continue our journey, reaching the red planet Mars. Now Mars is slightly smaller than the Earth, and it's considerably further away from our Sun. It's getting a bit colder now, the scaled-down solar warmth beginning to diminish. If we were to look at Mars in comparison to our Sun, it would probably be this tiny speck right here, a little more distant, a little less prominent. We're getting further and further away now, And these distances are going to keep growing, exponentially expanding as we venture further out into the scaled solar system. All right, we're getting pretty far away, now a considerable walk from our football-sized sun. And this marks the start of the asteroid belt. The asteroid belt contains millions of asteroids remnants from our solar system's early formation, and it's not a tightly packed field like in the movies. It's a vast, diffuse belt. It begins approximately here and would go on for about another 100 feet in our scaled model. Imagine that immense, scattered expanse of cosmic rubble. We're going to have a little stop here in the heart of the asteroid belt because it's home to a fascinating dwarf planet called Ceres. In our scaled model, Ceres would be about 277 feet away from where our sun was originally placed. Now, Ceres is a very, very small planet even in the context of dwarf planets. If I could point it out here, in comparison to the sun, it would probably be like this tiny pebble, a very, very small speck indeed. But we affectionately call it a planetoid because it's still quite big for an asteroid, and its own gravity has pulled it into a spherical shape. So I thought it worth mentioning here, as it's a quite interesting object to consider. Just to emphasize, this is the end of the asteroid belt in our scaled journey. If you can imagine how far we've walked, how many theoretical football pitches we've crossed, and then think about how many asteroids there must have been in that vast section. Literally millions. And we know about millions, but there are probably countless more still that we haven't discovered quietly drifting in the cosmic dark. While often depicted as dangerous, these asteroids are actually very thinly distributed. They can range in size from a tiny speck of dust, barely visible to objects many kilometers wide. But passing through the belt for a spacecraft is actually quite safe, as the average distance between significant asteroids is roughly 1 million miles in reality. Okay, let's continue. Jupiter is about 5 times as far away from the Sun as Earth is. In our scaled model from where we are now, Jupiter would be a truly significant distance. And from this immense distance, it's getting absolutely frizzy cold. Surface temperatures on the moons and the planets around here are profoundly cold, far from the life-sustaining warmth of the inner system. Now let's have a look to see how big Jupiter is in our scale. Jupiter is our biggest planet in the real solar system, a true behemoth. Yet even in this scaled model, it's still quite small in comparison to the Sun, perhaps the size of a golf ball next to our football. I really love Jupiter though. They call it the solar system's vacuum cleaner, an affectionate and apt description. Its colossal gravity acts as a shield protecting us from many of those rogue asteroids and comets, which, if not for Jupiter's gravitational influence, might otherwise come hurtling towards the inner planets, including our precious Earth. Let's keep going. We've just headed out to the football pitches now, truly emphasizing the growing distances. And this is where Saturn would be located. Saturn, apart from Earth, is my absolute favorite planet. Let's see how big it is in our scale. Just imagine, it has those magnificent rings, of course. Compared to the Sun, it's reasonably big, perhaps a tennis ball next to our football. Still smaller than Jupiter, but undeniably a substantial world. And yes, we're now about 939 feet away from where we started a truly significant journey on foot, a testament to the immense, sprawling nature of our solar system. Okay, so we've walked a truly considerable distance now. Our internal odometer reads 890 feet, and we've just come up to Uranus, or Oranos, however you prefer to pronounce it. For the cosmos allows for many accents. This is it in comparison to the Sun, which is quite funny really, because we consider these celestial bodies to be the majestic gas giants of the solar system. And as you can see, even Uranus is not really that giant in comparison to our football-sized Sun. It would be perhaps the size of a ping pong ball. But still, it is a very interesting planet, famously spinning on its side rather than rotating upright like the others. Don't know how to explain that. It's one of the charming mysteries of our cosmic family. Let's keep going. We're heading for Neptune now, the final planetary frontier. All right, we've walked quite a ways now, a truly epic stroll. We are an astonishing 263 feet away from our starting point, where our football-sized sun sits. That makes us a staggering 30 times further away from the sun than Earth is. And we're at Neptune now, which is again pretty similar in size to Uranus, perhaps another ping pong ball. It's a beautiful dark blue color shrouded in frigid winds. So we've come this far on our scaled journey. Now we approach the realm of the Kuiper Belt, a vast ring of icy bodies beyond Neptune. This region begins at about 3,000 feet from the sun in our scale and stretches all the way until 5,000 feet. It's an immense, silent, icy wilderness, and within this belt, we finally arrive at our beloved Pluto. In our scaled model, Pluto is about the size of this tiny bead, or perhaps a single grain of rice compared to our football-sized sun. This little thing here, this truly minuscule piece, is still considered the biggest object in the Kuiper Belt. The Kuiper Belt itself, as I mentioned, is mainly a lot of asteroids, but unlike the inner asteroid belt, it's composed primarily of ice and a few scattered rocks. We're about halfway through the Kuiper Belt now, and we still have quite a bit further to go. Even further out still within the Kuiper Belt, we encounter other fascinating dwarf planets. Take Haumea, for instance. Haumea is about 4,300 feet away from our sun in this scaled model. It's getting pretty freaking cold out here with surface temperatures dropping to unimaginable lows. If you were to imagine a tiny piece of dirt here that would be compared to that planet, it would be more likely like this microscopic speck. This little stone is so small, you can barely see it on the tip of my hand. If you compare it to our sun, it's truly like an invisible piece of dirt. Next, we journey to Makemake, only about 200 feet away from Haumea, still within the vastness of the Kuiper Belt, making it around 4,500 feet away from the sun. Again, this is not a place for humans to comfortably exist. It's a frozen, airless void. Its size again is similar to Haumea, another tiny distant speck. Finally, we reach the end of our huge Kuiper Belt, which is ginormous indeed, stretching from 3,000 to 5,000 feet from the sun in our scaled model. This is an immense, scattered asteroid belt, and we have finally reached its distant edge. But our journey isn't quite over, for the solar system extends even further. We now arrive at the furthest planet we know of, a dwarf planet named Eris. Eris is about 68 times further away than the sun to the Earth, so in our scaled model, it's truly an enormous distance, pushing beyond the 5,000-foot mark of the Kuiper Belt's edge. This planet is about twice the size of Makemake and Haumea, still not very large, but a significant icy world at the absolute fringes of our known planetary domain. These scaled models, from the grain of sand to the football, are invaluable tools for our minds. They collapse the incomprehensible distances into something we can walk, measure, and truly feel. They underscore the incredible emptiness of space, the vast gulfs between even our closest celestial neighbors. They highlight how much of our solar system is actually empty space, with small precious worlds scattered across immense distances. And in that vastness, the sun, whether a grain of sand or a football, still exerts its gentle yet all-encompassing gravitational pull, holding everything in its silent, majestic dance. This sense of scale is a humbling yet deeply beautiful realization to carry into the quiet of the night. As we drift towards the quiet close of our cosmic journey tonight, having traversed the immense distances and contemplated the profound origins of our solar system, let us engage in one final gentle act of exploration. The universe, in its boundless mystery, often presents us with phenomena that at first glance seem intuitive, but upon closer inspection reveal a far more nuanced and surprising truth. Our minds, though endlessly curious, sometimes form quick assumptions based on limited information. So let's take a quiet moment to gently challenge some of these common ideas, to illuminate the subtle truths that often hide beneath the surface of what we think we know about our solar system. This is an invitation to refine our understanding, to see the cosmos with a clearer, more discerning eye. Let's count down the top 10 common misconceptions about our solar system. See if you believed any of these before we gently uncover the deeper truths. 10. The sun is a burning ball of fire. This is perhaps one of the most ingrained images from childhood of our sun as a colossal bonfire raging fiercely in the sky. And while the sun certainly glows with an intense heat, it is not burning like a fire in the chemical sense we understand. Fire on Earth is a chemical reaction combustion where materials combine with oxygen, releasing light and heat. Our sun, however, glows for a far more profound and powerful reason. Its immense temperature, around 5,500 degrees Celsius at its surface, causes it to emit light. This incredible heat is not produced by chemical burning, but rather by nuclear fusion, a colossal nuclear reaction taking place deep within the sun's core. Here, at an unimaginable temperature of about 15 million degrees Celsius, hydrogen atoms are crushed together with such immense force that they fuse to form helium, releasing an enormous amount of energy in the process. As this staggering heat travels outwards through the sun's vast layers, it becomes much cooler by the time it reaches the surface, but still very much hot enough to glow brightly in visible light, bathing our solar system in its life-giving warmth. Just to give you a humbling comparison, a typical wood fire on Earth burns at a mere 500 degrees Celsius. The sun's surface is 11 times hotter, and its core, beyond all terrestrial comprehension, is 30,000 times hotter than that. 9. Pluto is the most distant and last object in the solar system. For many years, this was the accepted truth, a familiar boundary to our cosmic home. But as our telescopes grew more powerful and our understanding deepened, we realized that Pluto, while distant, is far from the final frontier. Pluto actually resides within a vast donut-shaped region of icy objects called the Kuiper Belt. This belt, a cold, dark repository of comets and dwarf planets, extends outward from Neptune's orbit, stretching far into the cold reaches of space. But even beyond the Kuiper Belt, there is another truly vast spherical region of icy objects called the Oort cloud, which, like the Kuiper Belt, is a distant home to countless icy comets. Furthermore, we've discovered that there are even 4 other dwarf planets that we know about that orbit further out than Pluto, and some are even larger than Pluto itself. These include Haumea Makemake, Eris, and Sedna. Eris, for instance, is currently about 3 times as far away from the Sun, as Pluto is truly pushing the boundaries of what we considered our home, and Sedna, which has not yet been officially classified as a dwarf planet, but almost certainly is one can reach an incredible 937 astronomical units away from the Sun. That, in other words, is a staggering 31 times Neptune's distance from the Sun. Some astronomers even believe Sedna might be the first known member of the inner Oort cloud, hinting at yet another layer of our solar system's colossal structure. 8. Saturn is the only planet with rings. The magnificent, shimmering rings of Saturn are undoubtedly one of the most iconic and breathtaking sights in our solar system. Captured beautifully by countless images from spacecraft like Cassini. And for many years, the popular imagination, and indeed, many school textbooks, held that Saturn was uniquely blessed with these amazing rings, made up of countless small rocks, ice, and other particles. However, this is a beautiful misconception. The truth is, there are actually several other planets that also have rings around them, though they are far less prominent and spectacular than Saturn's. In fact, all of the larger planets in the outer solar system, the gas and ice giants, have been found to have rings. This includes Jupiter, whose faint, tenuous rings, composed mostly of dust, cannot be seen from Earth without specialized equipment. Neptune also possesses a system of dark, narrow rings, and even Uranus boasts 9 bright, distinct rings around it, as well as a few fainter ones. However, all of these other planetary rings are incredibly difficult to observe from Earth due to their immense distance and their composition, which makes them less reflective than Saturn's icy spectacle. 7. Comets come from regions outside the solar system. The image of comets as rogue cosmic interlopers hurtling into our solar system from the vastness of interstellar space is a romantic one. However, this is largely a misconception. Comets are an integral part of the solar system. They are not foreign visitors from beyond our sun's gravitational domain. Scientists firmly believe they originate from one of two incredibly distant icy locations within our solar system. The comets that we see, relatively often perhaps every 100 years or so, are thought to come from the Kuiper Belt, the donut-shaped region of icy bodies just beyond Neptune's orbit. These are the short-period comets, their journeys relatively brief. However, the truly majestic long-period comets, those ethereal visitors that we see very rarely, perhaps only once every few thousand or even tens of thousands of years, are believed to originate from the incredibly distant and vast Oort cloud, the spherical shell of icy debris that completely surrounds our solar system, stretching almost halfway to the nearest star. These are the ancient wanderers, disturbed from their millennia-long slumber by subtle gravitational nudges, beginning their slow, majestic fall towards the sun. 6. Asteroids in the asteroid belt are very close to each other. Thanks to popular culture, particularly Hollywood space movies like Star Wars, we often harbor the impression that the asteroid belt is a densely packed, treacherous obstacle course where asteroids are constantly bashing into each other, and spaceships would have an almost impossible time navigating an asteroid field without being instantly obliterated. This makes for thrilling cinema, but it is a significant misconception. In reality, asteroids are not close to each other at all. The material within the asteroid belt is so incredibly thinly distributed across such an enormous volume of space that numerous unmanned spacecraft, including the Voyager's Pioneers and Cassini, have traveled through it without a single incident or collision. On average, the distance between any two significant asteroids is roughly 1 million miles, a vast empty expanse. To put this into further perspective, the total mass of the entire asteroid belt is only just 4% of the mass of our moon. It's far from a dense field. It's a vast, mostly empty region, sparsely populated by cosmic debris. 5. Mercury is tidally locked to the sun like the moon is to the Earth. For many years, this was a widely accepted belief among astronomers. It was thought that Mercury, being so close to the sun, was synchronously tidally locked with its star, meaning it rotated once for each orbit, always keeping the same face directed towards the sun, much in the same way that the same side of our moon always faces the Earth. This seemed logical given the powerful gravitational tides exerted by the sun. However, radar observations conducted in 1965 conclusively proved that the planet has a more complex and fascinating relationship with the sun. It possesses a 3-to-2 spin-orbit resonance. This means that Mercury rotates exactly 3 times for every 2 revolutions it completes around the sun. It's a subtle, almost rhythmic dance. The original reason astronomers initially thought it was tidally locked was that whenever Mercury was best placed for observation from Earth, a limited window due to its proximity to the sun, it always happened to be nearly at the same point in its 3-to-2 resonance, thus always showing the same face to our telescopes. It was an observational bias, a trick of cosmic timing, that hid the planet's true rotational secrets for so long. 4. Mercury is the hottest planet in the solar system. This misconception is perhaps the most intuitive. Given that Mercury is the closest planet to the sun, it seems perfectly sensible to assume it would be the hottest. However, this is simply not true. It turns out that Venus is actually a hotter planet than Mercury, even though it orbits further away from the sun. The profound reason for this lies in Mercury's lack of an atmosphere. Because Mercury is so incredibly close to the sun and has very low gravity, it has virtually no atmosphere. There is nothing substantial to trap the intense heat received from the sun. Its surface temperatures fluctuate wildly, with incredibly hot days and frigidly cold nights. Venus, on the other hand, possesses a notoriously thick atmosphere composed primarily of carbon dioxide, which acts like a massive opaque blanket. This dense atmosphere creates a runaway greenhouse effect, efficiently trapping the heat created by the sun. The maximum temperature you'll find on Mercury is around 426 degrees Celsius during its scorching daytime, but its night side plummets to 173 degrees Celsius. The average temperature on Venus, however, is a relentless 462 degrees Celsius. Hotter than the melting point of lead consistently across its entire surface day and night. 3. The sun only accounts for a small part of what's in the solar system. We intuitively know the sun is big, a colossal orb of light and heat, but most people vastly underestimate its true dominance. I'm sure you guessed the sun is massive, but the reality is truly humbling. The sun actually makes up over 99.8% of all of the mass in our entire solar system. Think about that for a moment. All the planets, including Jupiter, the king of the planets, all the moons, asteroids, comets, and every speck of dust combined constitute less than 0.2% of the solar system's total mass. Jupiter, with all its grandeur, and some of the other large planets make up most of the remaining tiny fraction, leaving our own Earth barely even registering in the equation, a mere cosmic dust mote in comparison. We can be profoundly glad the sun is as large as it is, though, as its immense mass is the fundamental reason why everything in the solar system works, as it does why planets remain in stable, graceful orbits, and why our Earth is constantly bathed in life-giving light, heat, and energy, all held together by the sun's massive, benevolent gravity. 2. Comets always have tails. When we picture a comet, the iconic image is almost always of a bright, luminous head with a spectacular streaming tail trailing behind it. This is true for many comets, but it is a misconception that they always have tails. Comets are essentially dirty snowballs or icy mudballs. They only develop their fuzzy shell-like cloud called a coma, and 1, 2, or even 3 distinct tails when they venture close enough to the sun. As a comet approaches the sun's warmth causes its volatile icy materials to sublimate, turn directly from solid to gas, releasing dust particles and gas. This gas and dust form the glowing coma around the nucleus. The comet's tail and coma become illuminated and may become visible from Earth when a comet passes through the inner solar system with the dust reflecting sunlight directly and the gas glowing from ionization by solar radiation. Interestingly, while the solid nucleus of comets is generally less than 50 kilometers across, the coma may be larger than the sun itself, and ion tails have been known to extend an astonishing 3.8 astronomical units. That's 355 million miles. It's also important to note a fascinating detail. A comet's tail will always point away from the sun, regardless of the comet's direction of travel, pushed by the solar wind and radiation pressure. When a comet is far away from the sun in the frigid outer reaches of the solar system, it remains a frozen, inactive chunk of ice and rock with absolutely no coma or tail. It's just a silent, dark wanderer waiting for its distant journey back towards the sun's embrace. 1. The solar system formed during the Big Bang, along with the rest of the universe. This is a profound and common misconception that merges two distinct cosmic events. While the Big Bang was indeed the monumental beginning of our universe, our solar system is considerably, immeasurably younger than the universe itself. According to current scientific research, the best estimate for the age of the universe is approximately 14 billion years. This is the moment when all of space and time began an explosion of creation that set the stage for everything that followed. Our solar system, however, is only about 4.5 billion years old. It is a relatively recent addition to the cosmic timeline. The solar system is said to have formed not during the Big Bang, but much, much later from the gravitational collapse of a giant molecular cloud, the very process we gently explored in our earlier chapters. The vast majority of the mass within that collapsing cloud coalesced to become our magnificent sun, while the remaining much smaller fraction formed everything else we find in the solar system: the planets, moons, asteroids, and comets. It's a testament to the ongoing processes of star and planet formation throughout cosmic history. long after the initial moments of universal creation. Thank you for joining me on this quiet journey through the wonders and nuances of our solar system. Making these contemplative voyages into the cosmos requires patience, long-term planning, and dedication, which we are only able to do thanks to the continuous support and gentle encouragement of our patrons. A huge thank you to everyone who has joined our cosmic family. And if you'd like us to continue exploring more videos like this, you can join us through the link below. When you join, you'll be able to watch all our videos ad-free, see your name in the credits as a fellow cosmic explorer, and even submit your own questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time, and until then, may your dreams be filled with the silent beauty and endless mysteries of the cosmos.